Population inversion is the condition in which more atoms or ions occupy an excited energy level N2 than a lower energy level N1. In ordinary thermal equilibrium, the opposite is true because the Boltzmann factor makes N1 greater than N2. The inversion factor is defined as delta N equals N2 minus N1. When delta N greater than 0, we have inversion. Think of a two-story building where most people are normally on the ground floor N1. A population inversion is like a crowd gathering on the second floor N2 while the ground floor is relatively empty, a situation that does not happen spontaneously but must be forced by an external pump. The simple criterion N2 greater than N1 is the cornerstone for any laser or maser, because only then can stimulated emission dominate over absorption. Statistical mechanics tells us how particles distribute among energy levels at a temperature T. The Boltzmann distribution gives N2 over N1 equals G2 over G1 times X negative open parenthesis, E2 minus E1 close parenthesis divided by K sub BT, where G are degeneracies, E are energies, and K sub B is Boltzmann's constant. For a positive T, the exponential is always less than 1, so N2 is less than N1. If we formally allow T to become negative, a negative temperature state, the exponent becomes positive and the ratio can exceed 1, achieving N2 greater than N1. Negative temperature does not mean colder than absolute zero. Rather, it describes a system where adding energy reduces entropy, that is, the population is already piled up in high energy states. This inverted population is precisely the condition required for laser action. The inversion condition can be written as N2 over N1 greater than G2 over G1, which is only possible when the effective temperature is negative. Rate equations describe how the numbers of atoms in each level change with time due to pumping, spontaneous decay, and stimulated processes. Two-level system. N2 equals W sub P N1 minus open parenthesis, a 21 plus B21 I close parenthesis N2 plus B12 I N1, where W sub P is the pump rate, A is spontaneous decay, B are Einstein coefficients, and I is photon intensity. This model shows that a steady-state inversion cannot be reached because any pump also raises N1, and stimulated emission quickly depletes N2. Three-level system. Add a ground state level 0, a pump level 2, and a lasing level 1. Pump quickly excites atoms from 0 to 2. Then rapid non-radiative decay 2 to 1 creates a population in level 1. The rate equations now include a fast decay term, tau 21 much less than tau 10, that helps keep N1 greater than N0. Four-level system. Adds a fourth level 3 above the lasing level 2 that decays quickly to a fourth level 0 that is essentially empty. The key advantage is that the lower laser level 1 is quickly emptied, so the inversion condition reduces to N2 greater than N1 approximately 0, which is much easier to satisfy. Real lasers, for example ND:YAG-He-Ni, are designed as four-level systems because the mathematics shows a much lower pump threshold. Pumping is the method used to move atoms from the lower level to a higher one, creating the inversion. Optical pumping. A separate light source, another laser, or a flash lamp provides photons of energy matching a transition from the ground state to a higher excited state. The atoms absorb these photons and later relax non-radiatively to the lasing level. Example, ND:YAG is pumped by an 808 nanometer diode that excites Nd3 plus ions, which then relax to the 1064 nanometer lasing level. Electrical current pumping. In semiconductor lasers or gas discharge lasers, an electric field accelerates electrons that collide with atoms, exciting them. In a helium-neon tube, a high voltage creates a discharge exciting helium atoms that then transfer energy to neon. Chemical pumping. Energy released from a chemical reaction directly populates an excited state. The hydrogen fluoride laser uses a reaction between H2 and F2 to produce excited HF molecules. Photoacoustic pumping. A pulsed laser creates a pressure wave sound in a medium. The acoustic energy can be converted into excitation of certain molecules. Though less common, it illustrates that any mechanism capable of delivering the right amount of energy to the right transition can serve as a pump. The small signal gain G0 of a laser medium is the exponential growth per unit length of a weak optical field, and is given by G0 equals sigma times delta n, where sigma is the stimulated emission cross-section approximately 10 to the minus 19 square meters for many solid-state lasers, and delta n equals n2 minus n1 is the inversion density. If the medium length is L and the mirrors have reflectivity R, same on both ends for simplicity, the round-trip gain must at least compensate for the round-trip loss. The threshold condition is G0 times L greater than or equal to the natural logarithm of 1 over R. Rearranging gives the minimum inversion density required. Delta n sub th equals 1 divided by sigma L times the natural logarithm of 1 over R. This formula shows why longer cavities or higher reflectivity mirrors reduce the pump power needed. They lower the required delta n. In practice, other losses scattering absorption are added to the right-hand side as an extra loss term. When the intensity of the laser field becomes comparable to the medium's ability to supply gain, the gain saturates. The saturation intensity is defined as I sub sat equals h nu over sigma tau, where h nu is photon energy, sigma is the emission cross-section, and tau is the upper level lifetime. For I much less than I subsat, the gain is approximately constant, small signal regime. As I approach as I subsat, the inversion delta n of t is depleted faster than it can be replenished by the pump, leading to a reduced effective gain, g of I equals g0 divided by 1 plus I over I subsat. This behavior can be derived from the rate equation for delta n. d delta n by dt equals w sub p minus delta n over tau minus sigma I delta n over h nu. Solving in steady state gives the same saturation law. The practical impact is that once the laser reaches steady state output, any further increase in pump power yields diminishing returns because the gain is clamped near the threshold value. Nd:(YAG inversion density. For lambda equals 1064 nanometers, sigma approximately 2.8 times 10 to the minus 19 square meters, and tau approximately 230 microseconds. The saturation intensity is I subsat equals hc over lambda divided by sigma tau equals 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by 1.064 times 10 to the minus 6. Over 2.8 times 10 to the minus 19 times 2.3 times 10 to the minus 4, approximately 1 times 10 to the 4 watts per square meter. If the cavity length is 0.1 meters and the mirror reflectivity R equals 0.99, the required inversion density is delta n sub th equals 1 over sigma L times natural log of 1 over R equals 1 over 2.8 times 10 to the minus 19 times 0.1 times natural log of 100 approximately 1.6 times 10 to the 20 per cubic meter. B He minus Ni pump power. The He minus Ni laser operates at 632.8 nanometers with an active gas pressure about 1 torr. The stimulated emission cross-section is about 3 times 10 to the minus 23 square meters, and tau approximately 100 nanoseconds. For a 5 centimeter cavity and R approximately 0.99, delta n sub th equals 1 over sigma L times natural log of 1 over R approximately 1 over 3 times 10 to the minus 23 times 0.05 times natural log of 100 approximately 1.5 times 10 to the 24 per cubic meter. The number of neon atoms in the excited state is obtained from the discharge current I sub d. The excitation rate per atom is proportional to I sub d divided by n gas. Typical discharge currents of 5 milliamps produce an inversion density around 10 to the 23 per cubic meter, so a pump power of a few watts electrical is enough to reach threshold. Explain why a two-level system cannot achieve steady-state population inversion under continuous pumping. Include a short rate equation argument. Strategy: write the two-level rate equations, show that the pump also populates the lower level, and that steady-state solution gives N2 over N1 less than or equal to G2 over G1, never greater than 1. Derive the expression for the threshold inversion density delta N sub th for a 4-level laser with mirror reflectivity R and cavity length L. Strategy: start from small signal gain G0 equals sigma delta N, Use threshold condition G0L equals natural log of open parenthesis 1 divided by R close parenthesis. Solve for delta N sub TH. A ND colon Y a G rod 10 mm long is pumped with 808 nanometer light, delivering 5 watts of absorbed power. Estimate the inversion density, assuming 30% quantum efficiency, and tau equals 230 microseconds. Strategy: calculate pump rate W sub P equals eta P sub abs divided by open parenthesis H nu sub P times V close parenthesis, where V is the pumped volume, then delta N approximately equals W sub P tau. Compare optical pumping and electrical pumping in terms of efficiency, typical pump sources and applications. Strategy: list pros and cons. Give examples: diode pumped solid-state lasers versus semiconductor laser diodes, helium neon discharge. For each problem, identify known quantities, write the relevant formula from the earlier sections, substitute numbers, keep track of units, and interpret the physical meaning of the result.